All right, time for section 3.4, zeros of polynomial functions. All right, let's buckle in, guys. This is going to be a long and involved video, but we can do it. We can get there. We will get there together, and it's with me, Mr. Hain. All right, so let's take a look at a couple of theorems to start off. So the possible rational roots theorem says that the factors of the constant term q and the factors of the leading coefficient p form a fraction, p over q, which equals all of the possible real roots of any polynomial function. So let's see what the heck that looks like. All right, really, for an example, let's take the first one, which is 6x cubed minus 11x squared minus x plus 6. So the constant term q is 6, and the without a variable x, and the leading coefficient is the coefficient of the term with the highest exponent, which again is also 6. So that means the factors of p are all of the factors, positive or negative, that would multiply to make 6. So 1 times 6 is 6, and 2 times 3 is 6. So we order them from least to greatest, and it's all plus or minus all of these values. You form a fraction with q as your denominator, and of course, since q is also 6, we have the same numbers. Now, every single possible combination, so 1 over 1, 1 over 2, 1 over 3, and 1 over 6, 2 over 1, 2 over 2, which is actually just going to reduce to 1, 2 over 3, and 2 over 6 would reduce to 1/3. So you're basically making every combination possible, numerator and denominator, with all of these and reducing them until you have this list of numbers. And that's a plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6, obviously. Plus or minus 2/3, plus or minus 1/3, plus or minus 3/2, and plus or minus 1/2. So these are all of the possible reduced to simplest form rational roots for this function, 6x cubed minus 11x squared minus x plus 6. This just gives us a starting point where we can look at and examine all of the possible roots for any function. More on why we would do this in a little bit. So let's take a look at this example. And what I'm going to do is I'm going to check to see if any of they are roots. So the easy way we learned in section 3.3 is by using synthetic division. So I'm going to check -1 and bring down the 6, multiply and add, and I can already see when I multiply -1 times 16, this is not 0. So it's not a root. So again, these are just possible rational roots. So let me check 1. So if I check the number 1, again, I set up synthetic division, bring down the 6, multiply 1 times 6, and then add, so I have -5. Multiply, and then add, so I have -6. Of course, now, if I multiply and add, then great, I actually have a 0. And of course, these are coefficients, and if I wanted to find the other zeros, I can use the X box and factor and use the zero property principle to actually see that I have all of these, which are going to be -2/3 and 3/2. So this is the zeros, 1, -2/3, and 3/2. And what do you know? 1, -2/3, and 3/2. They are in our list of possible rational roots. All of those are in our original list. So again, the possible rational roots theorem gives us a launching point when we have no idea how to factor something to just dive in and start factoring and solving for the zeros of a polynomial function. So Descartes' rule of signs is a rule, and it counts the sign changes in f of x and f of -x. And we use the -2 rule to tell us the number of possible positive or negative roots or zeros. Sounds so confusing. So let's just get an example. So let's take a positive f of x here, which is x to the 4th power minus 14x cubed plus 71x squared minus 154x plus 120. So we're going to count the sign changes. Now this is a positive x to the 4th power. The coefficient is +1, so that's 1 sign change. From negative to positive, that's 2 sign changes. From positive to negative, that is 3 sign changes. And then from negative to positive again, so we have 4 total sign changes. So this is where the minus 2 rule comes in. I have 4 as my total number of sign changes. So it could be 4, 4 minus 2 is 2, and 2 minus 2 is 0. So I have 4, 2, or 0 possible positive roots. I will not have 3 positive roots. I will not have 1 positive root. The only possible positive roots are going to be 4, 2, or 0. So I'll have all 4, 2 positive, and 2 negative, or I will have 0 positive and all negative roots. So to find f of negative x, let's examine closely. If I have an even index, so x to the fourth, so the fourth power is my index, negative x to the fourth power is positive. So any even index will just keep it the same sign, keep that term the same sign. However, any odd index exponent is going to change the sign. So this negative 14 becomes positive 14. 71x is positive, so it stays positive because that's an even index. X, if there is no exponent, the exponent is 1. So I'm going to put a negative x in here. It's going to change that sign. So now I have positive 154, sorry, it's 154, and plus 120. So while this might be a small mistake, the biggest thing that we're looking at is how many sign changes are in the f of negative x. And of course, there are no sign changes. So that means there are 0 possible negative roots for this function. So let's check this out. Let's take a look at another example. So let's count how many sign changes we have here. I have 1, 2, and then 3. These are both positive, so it's not another sign change. So by using the minus 2 rule, that means I have 3 or 1 possible positive roots. Awesome. So let's take a look at the negative. And so when I got the negative, it's going to change the sign of all of the odd indexed terms. So that becomes negative. The positive x becomes negative. And now I'm going to count sign changes. These are all negative, and this is the only sign change here from negative to positive. So I see 1 sign change, which means for the f of negative x, I could only have 1 negative real root. So what the heck is my answer here? So using Descartes' rule of signs, I see that I either have 3 or 1 possible positive roots, that's in blue, or 1 negative real root, that's in green. So what's the big idea? Let's apply this to a meaningful real-world problem. So I've got a sheet of cardboard. I've drawn a diagram here. It's made into an open box by cutting off its corners. So these are the little orange corners that we're cutting off. X represents the length of the side cut from the corner. So it's right here for how we cut it. And we want to know what size square must be cut to make a volume of 48 cubic inches. All right, so let's take this shape and I'm going to fold up the box and I'm going to get this shape here. And so the long side is going to be 10 minus these 2 x's. That'll be how long it is. And then on the short side, I have 8 minus 2 x's because I have this x and that x. All right, and the height of the box, as you see, is just how long that square is. So the height of the box is x. So how do we find the volume of a rectangular prism? We're going to multiply those 3 together. Length times width times height. So that gives me the length, which is 10 minus 2x here, times the width, which is 8 minus 2x, which is here, times the height of the box, which is the length of the square, x. All right, so this big idea problem. All right, so now we're going to look at actually taking this and simplifying it into a function. So I'm going to multiply and FOIL out everything on the right-hand side. And then I'm going to set it equal to 0. So I'm going to move the 48 over and then move the 0 over to my far right just because that's what makes sense. That's what we've been, it just kind of makes sense in our head a little bit better. And here I noticed something, 4, 36, 80, and 48. These are huge coefficients, and I can factor the 4 out. So now 4 times something equals 0. So I can divide both sides by 4, and I just have x cubed minus 9x squared plus 20x minus 12. This function models the volume of this box given any length of the square that we cut out, if we make it equal to 48 inches, cubic inches for the volume. So this black formula here, x cubed minus 9x squared plus 20x minus 12, This is going to be what drives the rest of our discussion. So we need to try and factor and find the zeros of that function. This is a big task. And really we need to use the tools that we just learned to attack this problem. So we're going to use the possible rational roots theorem, and we're going to see what are the possible values that x could be so that we can start dividing using synthetic division. So p, of course, is going to be the coefficient of the constant term, and q is going to be the coefficient of the leading coefficient, or the factors of the leading coefficient. And here, negative 12 is what I have the factors of for p, and q I have just 1. So for 12, I have plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, and plus or minus 12. 1 times 12 is 12, 2 times 6 is 12, 3 times 4 is also 12. And of course, all of these numbers divided by 1 means that I only have a list that is 12 roots long, because I have both the positive and the negative. I don't know about you, but I want to cut down the number of roots that I have to check. And to do that, sometimes we can use Descartes' rule. So we're going to take the original function, we're going to count the number of sign changes. 1, 2, 3 sign changes. That means I have 3 or 1 possible positive roots. Now for f of negative x, remember any odd number indexed term is going to change its sign. So both the positive x cubed and the positive 20x are going to change both to negative. And that's awesome, because you can see in the orange there are no sign changes, so there's no negative roots. That means all of these possible roots that we have to check, I only have to check the positive numbers. Now I only have to check 6 of them. It's a heck of a lot better than 12. All right, so let's check the roots with synthetic division. So we have a list of roots to check and a function to check it in. So I'm going to check 1. Here we go. Line them up, bring down the 1. 1 times 1 is 1. Add that to negative 9 is negative 8. Multiply and add. So I've got 12. Let's multiply 1 times 12. And the very first root that I check, I got a 0. Yes. So x equals 1 is a 0. And it gives me a quadratic function that I can now factor. Since a is equal to 1, I know that if I just throw it in the x, I can get my 2 terms. So those are actually what gets the other binomials. X minus 2 times x minus 6 gets me x squared minus 8x plus 12. And the zero product principle gets me my 2 other roots, positive 2 and positive 6. And lo and behold, 1 is a 0 on this list. 2 is a 0 on this list. 6 is a 0 on this list. So now we found all 3. And actually, if you recall, I'm going to rewind real quick, that I have 3 or 1 possible positive roots from Descartes' rule. So this, in fact, validates and proves Descartes' rule that I have 3 possible answers, 1, 2, and 6. Awesome. This means I can actually just check the solutions and I can have a final answer. So remember, the volume must be 48 inches cubed. So I'm going to plug it back into the original volume, length times width times height, and I'm going to substitute them in. So if I substitute in 1, awesome, I get 10 minus 2, because 2 times 1 is 2. If I'm plugging in 1 for x, then I also have 2 times 1 again, which is 2. So now I have 1 times 8 times 6, which is 48. Huzzah, it works. Huzzah, such an underused term. All right, so now I've got, I'm checking for my second root, which is 2. So I substitute 2 in, so I have x is equal to 2. 10 minus 2 times 2 is 4. 8 minus 2 times 2 is 4. So I simplify this. 2 times 6 times 4 is 48. So a 2 inch by 2 inch square also works. So that leaves us with 6, which is our last root. And if I multiply, I mean x is equal to 6, no problem. 10 minus 2x does give me a negative number. 10 minus 12 is negative 2. 8 minus 12 is negative 4. Yeah, if I multiply these together, I get positive 48, but it doesn't make sense. Remember that my box only has 10 inches. How can I cut 2 6-inch squares? That would leave me with negative 2 inches of box. On the short side, it would leave me with -4 inches of cardboard. They're negative lengths, so a 6-inch by 6-inch box does not work. Which means I only have two correct answers. There's two possible answers for the big problem, and that's a 1-inch by 1-inch and a 2-inch by 2-inch square. Oh my gosh, this is powerful. We've used the two theorem and a rule put together to kind of give us a launching point to check possible roots, using synthetic division from our previous chapter to plug them in and see if they are roots by remainder theorem. And by putting that all together and checking back in our original function, we can see we only have two answers. 1-inch by 1-inch and 2 inches by 2 inches. Yes, I'm excited because this is a real world example. I'm a math teaching geek, and so this makes me super duper happy. Okay, so the linear factorization theorem. So in bright pink, I have it written down. This is going to look odd at first. Yep. So what? What does this mean? Roots are possibly real. They're not necessarily distinct. If any roots are complex numbers, then the a plus or plus b times I and a minus b times I are... All right, hold on. We got to get an example. This means the nth degree polynomial. All right, linear factorization theorem in red. The nth degree polynomial can be expressed as a product of non-zero constant a, which is right here at the beginning, and n linear factors. So if I have a 4th degree polynomial, there will be 4 factors in a row. That's all this means. This ... lets us have how many different factors it is. All right. So I said it would look odd. It looks a little odd. Let's get to go what this means. So here's a question. Find the 3rd degree polynomial with real coefficients that has -3 and I as zeros. All right. I have a coefficient I don't know anything about. And then I have x plus 3 as my first term. Why? If I put in -3 to my first term, -3 plus 3 is 0. So I know that that must be 1. I, in any imaginary number, comes in conjugate pairs, which leads to x plus I and x minus I. All right, this is great. Because I is a root, again, I'm just reiterating. I have x plus I and x minus I. I'm going to FOIL. When I FOIL those, it goes to x squared plus 1. All right, so I'm going to continue to multiply. And now I've got to FOIL x plus 3 times x squared plus 1. So that gives me x cubed plus 3x squared plus x plus 3. All right, and that's times a number. A lot of times students will stall out here. And in fact, I forgot to write this down here. But the other piece of information that I have to give you is the value of this function, this f of x, at some number when I plug in an x. So this function is going to equal 8 when x is equal to 1. So I've substituted in 1 for each of these. So 1 cubed is 1. 1 squared is 1, so 3 times 1 is 3. If x is equal to 1, then this is a 1, and I bring down the 3. So here, I know that I can solve 1 plus 3 plus 1 plus 3 is 8. So in order to make this statement true, I divide a must equal 1. So because as a is equal to 1, when I put a is equal to 1 here and I distribute, this cubic function stays the same. So my answer is just f of x is equal to x cubed plus 3x squared plus x plus 3. All right, that's a mouthful. I highly suggest you rewind and make sure that you watch how I go through here. Remember, the one thing that I have here is that I am plugging in x equals 1, and I am telling you that the value is 8. I'm not just pulling these numbers out of thin air. So let's look at a better and a little bit deeper problem with linear factorization. So we've got some things popping up, but let's walk through. Let's get a 3rd degree polynomial where 6 and plus 5 or -5 plus 2i are zeros. And here the f of 2 is -636. All right, so these preview statements, if you will make more sense as we go along. All right, so let's make our function. A is always going to be there. So since 6 is a root, x minus 6, or the opposite sign, is going to give us our first term. And now I have -5 plus 2i. So I'm going to just make these the conjugate pair. So plus or minus the imaginary term. And yes, I did change the sign, but it's the imaginary term that needs to have the signs changed. Now, when I FOIL out these two here, the imaginary terms, that's what this preview statement was looking like. All right, x times x in black is x squared. X times 5 is going to give me 5x. X times negative 2i will give me negative 2ix. Okay, let's go to the 5. So 5 times x will give me 5x. 5 times 5 will give me 25. Negative 2i times, or I'm sorry, 5 times negative 2i will give me negative 10i. All right, that's the middle term. Now the red terms at the end, I'm going to multiply the positive 2i. So positive 2i times x, positive 2ix. Positive 2i times positive 5, positive 10i. And positive 2i times negative 2i, here we go, negative 4i squared. Now recall from one of our earlier videos that I squared is the square root, or I is the square root of negative 1. So I squared will just be negative 1. All right, so I've circled some terms here. Negative 2ix and positive 2ix, those cancel. Negative 10i and positive 10i, those cancel. Excellent. This means that I have x squared, 5x and 5x make 10x, and 25 plus 4 gives me 29. All right, this is fantastic. So now what I have is I can actually just FOIL out the x minus 6 with this one. It's a lot of work, but I get x cubed plus 4x squared minus 31x minus 174. So here, this is where this value comes into play, and it's in the same bright purple or bright pink color as I had before. So in the question itself, f of 2, which means I'm going to put the 2 in for all the x's. So 2 cubed is 8. When I put the 2 in here, 2 squared is 4. 4 times 4 is 16. 2 times negative 31 is negative 62, and of course 174 stays the same. All of these things have to equal negative 636. Now when I add these together, I get negative 212. And when I divide, the other preview part of this video popped out. And I have negative 636 divided by negative 212 is positive 3. Awesome. Now since a is equal to 3, I'm going to put this back here and I'm going to distribute. So 3 times each of the terms is going to give me my answer. So I distribute and I have 3x cubed. 3 times 4 is 12x squared. 3 times negative 31 is 93, and 3 times negative 174, of course, because you know your 174 times tables, is negative 522. Oh my gosh, get there. Linear factorization theorem, deep, meaningful, an awesome way to kind of take zeros and work backwards to find the function. Remember, I have to give you this statement. And in the previous slide, it was the f of 1 is equal to 8. And in this slide, it's f of 2 is equal to negative 636. So we've got a lot of stuff happening in this video. But that is the zeros of polynomial functions, ladies and gentlemen, with Mr. Hain. This is going to definitely warrant a watch through and following along with all of those notes to make sure that we know what is happening.